Was there any response?
No, sir, not yet. I can start in 2 minutes at 3:35.
Okay, so I think 3:35 will start. Yeah, I think you can start.
Okay, yeah, I'll start then. Just share. Yeah, so can you see my screen?
Yes, I can see it.
Okay. Yeah, so I'm just going to talk about the proof for the simplex method, the proof of termination. So yeah, I won't go over the method that much. This I've just gotten from your slides as well. So the goal is to basically given a formula of given a formula, we want to check whether it's satisfiable or not. So to do this, we introduce two new variables, phi a and phi prime, and then so we basically introduce these variables and have equalities in phi a, and then the inequalities for the additional variables in phi prime.
Mm-hmm.
Now, yeah, so we partition these variables into two disjoint sets, B and N, which are basic and non-basic.
Go back to your previous slide. Just one small question. Of course, I mean, you have shown a formula which is
yeah.
not.
So this one has also. Yeah, I realized.
Yeah, but your algorithm is only for conjunction.
It is only for conjunctions. Yeah.
Yeah. Okay. Good.
Yeah. So now, yeah. So B is the set of basic variables, N is the set of non-basic variables. And now, so the constraint AX equal to 0 can be maintained as a tableau. At, so yeah, which is basically you have Aij is the matrix values, and it can be maintained like this. Now, beta is a mapping that assigns a rational value to every variable. So this is the assignment that we want to find, which satisfies all the constraints, so that we find a solution, or we say that it's unsatisfiable. So now, yeah, these are the auxiliary procedures in between. So pivot and update. And the main algorithm is this. So the main algorithm basically selects the smallest basic variable that violates its bounds. And depending on how it violates, it looks for a xj, it looks for a non-basic xj that can whose assignment can be changed so as to satisfy the bounds for xi. So if such an xj is available, then we update it and pivot the two, change them, put xi in non-basic and xj in basic, and then of course update the tableau as well accordingly. If there is no such xj like this, then we return unsatisfiable. So this is the main algorithm. This we have already gone over, so I won't spend too much time. Now, so yeah, so these two things, which is basically the bounds on non-basic variables are always satisfied by beta. So this is due to based on the two procedures, the pivot and update, based on the pivot and update and the algorithm, this is always satisfied. And now since this invariant is satisfied,
That's always
also,
satisfied. Yes, correct. I mean, how about the initial state? Yeah. So in the
yeah,
initial
so
state,
in the initial state, the LJ and UJ are set to minus infinity and plus infinity, and beta xj is set to 0 for all j in this is for all non-basic non-basic variables.
correct. So, but in the initial state, if you set all of them to 0, some of the
Yeah,
non-basic variables, I mean, that condition that you showed above can be violated. No.
which the invariant, what
Yeah, the above invariant,
yeah,
you said all non-basic variables will satisfy their constraints, can get violated in the initial state if you initialize on some of the non-basic variables in the initial state, they may get
but we are in
violated.
this case we're
So,
initializing it specifically like this. So we are initializing it as in the initial state, the bounds are minus infinity and plus infinity, and all of them are set to 0. So that's the way we're initializing it. So that's why.
yeah, but okay, so this is just a small question. So what if for some in the initial state, the non-basic variables are the program variables, correct? Okay.
Yeah, correct.
Not the auxiliary variables. What if my question is, what if one of the program variables had a constraint whose, which is not minus infinity to plus infinity, if there was a finite?
Yeah, so you mean suppose it had something like x greater than 4, suppose. So in this case, we'll just introduce a new
lower
variable.
limits, yes.
Yeah, so we'll just introduce a new variable s and say s equal to x, and then add this in the phi a, and also then add.
Yeah, so that is one way. Yeah, so then you can get that to the thing. So
yeah.
our optimization is that you could then choose the initial assignment appropriately. Okay, so, you can set x in that case to 4. That's also you could do. Yeah, so you don't have to have it 0 all the time, is what I'm saying. Yeah. Okay.
Yeah. Okay.
So then you don't need to introduce additional auxiliary variables. Okay, that's the observation I'm making. I mean, what you said is also correct. Yes? Yeah.
Yeah.
So Harsh is here. Good. Go ahead. Yeah.
So in fact, the reluplex example that we had seen was something where there was a non-basic variable with an initial bound of not minus infinity to infinity, right?
Yeah. So yeah, I think there are two ways. I think this is kind of glossed over in some of those things. So there are two ways to handle it. I mean, one is to choose the initial assignment to be not all 0. Okay, but you could choose, you could choose the initial assignment such that those constraints are satisfied. You can always do that because they are program variables. They are not dependent on each other. Okay, at that point. Yeah.
Correct.
Yeah, or what Ameya said, you can introduce just a new auxiliary variables and equate them, okay, and and then transfer the constraint on the program variable to the auxiliary variable to which it is equated. Okay.
Yeah.
Okay, go ahead.
Yeah. So for the proof of termination, we really need the total ordering on the variables. So this we'll see why later, but this is important. Now, so basically first to just show that it's correct, which is show that the algorithm is correct. That is that if the algorithm does output satisfiable, then the formula is indeed satisfiable. So this actually you can get, this is obvious from these two properties. And these two properties can just simply be proved by looking at this algorithm. So the way it updates it is basically so when you pivot xi and xj, it doesn't change the ax equal to 0 still holds. Ax equal to 0 still holds even for beta as well as the new beta. So this is a constraint that is always satisfied, as well as invariant that yeah, as well as this is always satisfied. So if it does give satisfiable, that means that this is all the xj's are within their respective bounds, and so if that's the case, then the algorithm is correct. So that is just a simple thing. So now the main part of the proof is to show that it terminates. So yeah, so to show that it terminates, we first have to show that the number we first define
Yeah, but before you get to Ameya, so before
yeah.
you get to the details of the termination proof, I have one question. So go back.
Yeah,
or maybe I'll ask this question later on. Okay, so because one other observation, maybe you will get to that you want to make about the algorithm. Go back. Yeah, no, go to the invariant. So it is true that for all the non-basic variables, this is preserved. And that's why when it terminates, if all the basic and the non-basic variables satisfy, I mean, all the basic variables satisfy the constraints by this invariant, it automatically is it is sat, correct?
Yeah.
So that's what you're saying. So that is fine. So there is a stronger invariant that you can actually say about the non-basic variables. Correct? So as a matter of fact, it is when you pivoted the algorithm. I mean, you adjusted such that the basic variable that enters the non-basic variable set is set to, it is adjusted just enough, okay, to either LJ or UJ. So because the increment, so that is also is something that so the non-basic variables not only satisfy these things after each iteration, either additionally they are set to either LJ or UJ.
Yeah, so that is there in my proof. It comes later.
Okay, so that is okay. Yeah, I mean, I thought that is okay.
Yeah, I think it's right here. So basically, for any, so this is what you were talking about. I think for any non-basic variable and any key,
Yeah. Okay, that's okay. So I'm kind of moving way ahead of you. So I'll let you go. Yes.
Okay. So basically, every iteration of this algorithm, it modifies the assignment and the set of basic and non-basic variables, and it also modifies the current tableau. So for simplicity, I'm not going to write aij_t. Not like when it comes later. Also, I'll just refer to it as aij. But it is for the specific specific iteration. There's a separate tableau based on what are the basic and non-basic variables. So one observation is that there is a unique tableau for any set of basic variables, because all these tableaus satisfy the constraint ax equal to 0. And so so this is just an observation. Now we denote by st, which is a pair of beta t comma bt. We let this represent the state of each state of the
but this is an important observation. That's why I want to make sure that if Harsh understands, why should this be a unique tableau? Because did you get that, Harsh? That
no, sir.
So then can you explain, Ameya? So why should this be, the tableau should be unique?
So so what is a tableau? Tableau is basically
convince Harsh, okay, that it is. Yes.
Yeah, so it's basically a set of equations. So in so the set of equations is basically xi is equal to summation of xj belong to non-basic and aij into xj. So this is these are the set of equations. Now, this basically satisfies ax equal to 0. So now whenever we change whenever we update the tableau, we are not actually changing this equation. We are just changing the assignments to the equation and we are just moving it around.
That's right. So you are
we are
just moving it, from the left to the right.
We are just moving it from the left to the right. So it doesn't change the actual equation. So it always satisfies x equal to 0. So that basically that means that for any set of basic variables x, for any set of basic variables, you'll only have a single representation in this form.
Correct.
Okay.
Did you get it, or should I?
Maybe you can draw. I mean, you could just take a 2-variable example and just 2 equations and then illustrate to Harsh.
Suppose I guess we have this and yes. So let's say we have this now. So for this set of
so here the basic variables are
y and a.
Y and this is a or
a, yeah.
Y and a, and the non-basic is
X
and z.
Correct.
Z. Okay.
So now there is no other. So we cannot change these equations in any way such that you'll get y and a as basic, and you'll have a different set of non-basic things, right? So even if now suppose I pivot y and x, so then we'll get x is equal to y minus 3z and a is equal to y minus 3z plus 2z, so y minus z. So for any set of so basically what we're doing here is we're just moving it around. So if the left hand side is for any particular left hand side, this is same, it doesn't change. So we cannot have y and a as basic variables and have a different
I mean, you're saying that you can't change basic variables and you can't interchange basic and non-basic variables.
You can interchange basic and non-basic, but for any given set of basic variables, what are the non-basic? It is just the set of all variables minus those basic set. Okay. So for any set of basic variables, the non-basic set is fixed, which is the universe of variables minus the basic set. Okay. So so the non-basic for a given basic set, the non-basic is fixed, and then the way you derive equation is just by moving things from left to right. Therefore, there's a unique set of equations in terms of which you could express any basic variable in terms of the non-basic variable, because these equations is fixed. Okay. So how else, if you constrain yourself to move things between left and right to preserve that equation, how else can you and the non-basic set is the basic set minus whatever the variables in the thing. So that way, so this matrix for any given left-hand side is unique, okay, which is obtained from that original set of equations with variables moved from left to right. Yeah.
Okay.
Yeah. So yeah. So
Okay.
now we represent. So we look at a state at time step t. So that this state consists of the assignment beta t and the set of basic variables at that point. Yeah. So now, yeah, we also denote by nt, like sir said, the set of variables minus the set of basic variables is basically the set of non-basic variables. So we let S naught denote the initial state, where S naught is B naught and beta naught and B naught. Now, so this was the invariant that I was talking about before. What, sir?
No, what is your state? How do you define your state?
Yeah, so my state is defined as.
Okay. Yeah, because the non-basic set is determined by
the
basic set
set.
uniquely. Yeah, and the tableau, you remove the tableau because the tableau is unique. Okay, so that is for a given basic set, the tableau is unique. So you don't need to keep that information as part of the state.
Yeah, it also stores. I mean, it also stores all the constraints on the variables. That is, it's the same constraints, but it stores them as well. Now, so now this was the invariant that Sir was talking about, which is which basically says for any non-basic variable, we have either it remains unchanged, so it is equal to the assignment that was given at its initial state, or if it does, if it is changed, that means it comes from a basic. It comes from the basic set. So when it comes from the basic set, the way we have updated. So if we go back to the so we go back to the algorithm here, or rather, where is the update? Yeah, so we update it as we increase it by exactly li. So we pivot and update. So if it is violated, if it is less than, rather if the basic variable is less than its lower bound, then we increase it to be equal to its lower bound. If it is greater than its upper bound, then we decrease it to be equal to its upper bound. So that is basically why if we come here, it is, so this is an invariant that is satisfied. Now, so for any basic variable in xi belong to bt, we have bt, we have beta t of xi is equal to a summation of xj belong to nt aij beta t xj, which is basically just the tableau. So this is where I meant that I won't specify aijt, but this is technically aijt. So so where the constants aij are the tableau coefficients in st. So now another important observation here is that beta t xi is now uniquely determined by bt and the values beta xj. So we know beta xj can only have 3 values, so which is either beta naught xj, lj, or uj when xj belongs to nt, and and bt determines the tableau, since there's a unique tableau for each bt. So so then there are finitely many possible assignments beta t for a given bt. Since the number of variables is finite, there are finitely many possible sets bt as well. So therefore the states.
Okay, so now here this is very important. Okay, so I want Harsh, to also understand that. Go back to your was it the previous slide where you said beta t is unique. Okay, so that's very important. Okay, so no, next slide.
Like I had a question. So like, so for till now, like we have what we're kind of doing is trying to solve we are trying to prove that this thing terminates, right?
Yeah, so we're trying to prove that it terminates. So to prove that, first we'll prove that the set of states that it can reach is finite, and then we'll prove that it cannot have a cycle. So that will basically prove that it has to terminate.
Okay, and so and that we are trying to do some so what is the so this is about the reluplex algorithm, right?
No.
Simplex.
The simplex.
Simplex.
Oh, sorry. Yeah. Okay.
Okay, this is basic simplex. Okay.
Yeah.
So you want to show that basic simplex algorithm is going to terminate.
Yeah.
So and now you're showing that now you've shown that that tableau you first of all replace all that stuff of variables you basically wrote a tableau in terms of non-basic variables and then show that it is unique.
Yeah, so for a set of basic variables, it is so that That is what I had here, I think, right? Yeah, so there is a unique tableau for any set of basic variables B. So this is what this explanation was for, right?
By Tableau we mean like it's the
So we
set of
mean this set of equations, basically. So for each
equation, right?
yeah, so at each time step, we'll have a BT and an NT, and we'll have a separate tableau. So each, like these AIJs will change because you'll be
Okay.
moving it around, right?
Mm-hmm. So you basically write xi in terms of a lot of like you basically write xi in terms of that basic uh, e- in terms of these variables, right?
Correct. In terms of the non-basic variables, each
In
basic
terms of
variable
non-basic
is
variables.
expressed in terms of the non-basic variables. Okay.
Okay. Yeah.
Therefore, that tableau is unique for a given set of basic variables.
Yes.
Okay?
Yes.
And
Because
since
yeah.
and what Ameya observed was that the different possible BTs, so the different possible BTs is finite. Why? Because the number of possible basic set is also finite. Okay.
Yeah.
So for every set of basic variables, which are a subset. Okay.
So like this beta t, what is this beta t?
Beta T is the assignment given to, so in like for over here, so a satisfying assignment in this case would just be 0, 0, 0, right? So we'll have beta, so beta in this case, beta of y is 0, beta of x is 0, beta of z is 0. So beta is just an assignment that, that satisfies this tableau. So now we also have, so this is just one, so this is basically the phi a part of the thing. So now we have phi prime as well, right? So phi prime is the part where the additional variables, the m additional variables, so which are in the start, the basic variables, so they have bounds on them. Like, so in this example, I don't think that example is great because it has, but if you ignore these conjunctions, basically you have, ignore the disjunctions. We basically have, this is the phi a part, this, and the phi prime part is where you have constraints on the s's, which are the additional variables. So these are the basic variables at this point. Yeah. So where was I? Yeah. So so basically we are just trying to show right now that the set of states.
Go back. I still want to go back one slide. Yeah, it's the last bullet. I want to make sure. See, the assignment beta t is uniquely determined by BT. Okay. And BT itself is uniquely determined by, I'm sorry, the tableau is determined uniquely by BT. And for any beta, the beta T assignment for any BT is a unique, any assignment for beta T. And that's what is given by the third bullet, okay, as what Amir explained, okay? Because there's it's either LJ, UJ, or beta 0. So, or the initial value. So they're only finitely possible values in combinations, and therefore, the assignments that the algorithm considers for
so the possible assignments are finite, and possible BT's basic variable sets are also finite. So therefore,
these LNUs are upper and lower bounds, right?
Yeah.
Like just a question, like why can't the values be in between?
Yeah, so that is due to the algorithm. So
you're always either putting the upper or lower bound.
No. So go back. So it's only for the basic variable, the non-basic variables that they are between those two things. At any given point, the non-basic variables can be either at UJ, LJ, or the basic variables. It is uniquely determined. They don't have to be at LJ or UJ. Okay. they'll be in between.
Sorry, your voice got cut. Could you repeat the last line?
Yeah, I think, sir, your voice is cutting.
Oh, no. What I said was, no. Harsh asked the
Are?
variables be the assignment for some variables be between LJ and UJ. Okay. It is indeed possible, but if it is, that has to be then the basic variable, not the non-basic variable. So this constraint is only for non-basic, as as Amaya said, for any given non-basic variable at a particular time. This is the case. Okay.
Okay.
And so the different possible variables that can assume the role of a non-basic variable is finite.
Correct.
Then, for any given set of basic variable, the tableau is uniquely determined. So even if the basic variables can take something in between, but they are uniquely determined by this. Okay, so you could take all possible non-basic and basic variables, possible sets, and for each of them, you will get one unique beta t.
Okay.
But since the variable set is finite, therefore the variable non-basic set, any possible basic and non-basic, they are only finitely many subsets.
Yes. So
therefore, I was only pointing to the thing you said that, could
hello.
Jay, it can, but if it does, then at that point it will be in the basics.
Basics, yeah.
Okay, it makes sense. Like it's due to the algorithm that we are selecting these. Okay.
Yeah.
But I think this is where is something that for me at least. See, I had made the observation that I told that I would be asking this question. Therefore, the algorithm only goes through this.
Hello, sorry, your voice is breaking.
Okay.
We couldn't hear.
Is it better now?
It is better sometimes, and then it suddenly gets off.
Okay, so I'll try to be close. So what I'm saying is that the set of different assignments it considers, the algorithm considers, searches through is only finite. Okay. That raises the question, since an LP which can have infinitely many possible satisfying solutions. But how come you can get, if the possible satisfying solution is infinite, because it's a closed space, okay? Why is it okay to only look at finitely many assignments? Okay, so that's a question that we later have to get into, but nonetheless,
I think it's maybe because it's because that you only need to look at the endpoints in the simplex or something like that.
At least for some, you're right, correct. At least for some subset of any satisfying solution to a conjunctive thing, which is if it's a closed space, then some subset, you can always find a solution such that some subset will have the extremity points. Other.
Hello.
Yeah, and that's why it is enough if you're only wanting some satisfying solution and to check if it is satisfiable or not. then you can restrict yourself to that. All the other ones you can get by scaling, etc. Okay, other solutions also. But so the simplex algorithm, it goes through only a finitely many satisfying solutions in its search. Okay.
Yeah.
So I realize that we are not recording. Should we record?
I
thought you were
did
live
turn on the
streaming.
live thing. So, but I will record from here onward anyway, because usually the live stream. Yeah. Okay, now we have both. Sorry.
Okay. Yeah. So as sir pointed out, because there are finitely many possible assignments beta t and a finite number of subsets of bt possible. So therefore, the set of states is finite. So now, if the set of states is finite, then the only way that check will not, this procedure will not terminate is if there is a cycle. So cycle basically means that you have a subsequence of states sk to st plus 1 with st plus 1 equal to sk. So this, now we'll try to prove that this is not possible. So now to prove this, let's let xr be the largest variable in the variable ordering. So like I said, we need a total ordering on the on x1 to xn. So let's assume that xr is the largest variable in the variable ordering such that xr becomes non-basic in one of the states sk to st. So for all variables that become non-basic from basic in sk to st, xr is the largest in the variable ordering. So so now let's assume that this happens at time t. So we have that xr belongs to basic in bl and it belongs to nl plus 1. So it becomes non-basic at time t, or time l, sorry. So now since xr becomes non-basic in this state, we must have that
So let's back up a little bit. Okay. Now, what you're saying is, firstly, these states, each of them has a particular assignment, variable assignment, and a basic variable. So when you say st plus 1 is equal to sk, the two components are identical.
Yeah.
So they have the same basic set.
Yeah, beta t plus 1 is equal to beta k, and bt plus 1 is equal to bk.
Yeah. So which means, so between sk and st plus 1, several variables in B that are in bk can go out and come back, but whatever goes out will have to come back eventually, right? If there is a cycle.
Yeah.
So that's why. So you pick, among them, you pick the largest variable that gets out of the basic set, and it has to come back. Yeah. Okay.
Yeah. So it comes back. So we'll get to that. So it does come back in state SP. We'll get to that in the next slide, I think. So let's assume that in SL it first becomes non-basic. So now, if it becomes non-basic, that means it was violating its bounds as a basic variable. So it's either lesser than LR or it's greater than UR. The beta L of XR is either lesser than LR or greater than UR. So now for
yes, go slow there. So is that clear, Harsh?
Yes, sir, it is clear. Like we are just going to now prove that there are no cycles. And first, like if something
I was specifically pointing to that bullet in which Ameya just said that these either should be this or this. Why?
I assume that it is because of the algorithm which turns the thing into non-basic.
Yeah. So basically, here. So this is because of the algorithm. So we select the
Correct. Yeah.
yeah.
So if it's clear, you can move on. So if it's clear for Harsh, we can move on. Yeah.
There's one question, like, why does it switch from basic to non-basic? Like, how do we know?
No, we are assuming that. So no. So based on these sets, we are assuming that some variables move from the basic to the non-basic set, right?
Okay.
That we are going from, we are progressing in states. There is some change that is happening.
Okay, and you picked up the largest one.
So from out of all the variables that go from a basic, from basic to non-basic, we are saying that XR is the one in the XR is the largest in the variable ordering. So like I said, there is a total ordering on the variables x1 to xn. So we're assuming that XR is the largest in that ordering, such that it becomes non-basic in one of the states SK to ST.
Okay. And it becomes non-basic, so it must violate the some bounds.
Yeah.
And, yeah. Okay.
Yeah, sir, you were saying something?
No. I mean, eventually what Ameya will show is that if there is a cycle, assuming there is a cycle, something will go wrong. Okay. So in trying to prove it, is picking this, is using this XR, okay, the largest among the variables that move out of the basic set and then come back, okay, to do that. Correct, Ameya?
Yeah.
Okay.
Yeah, so we'll use, so right now we are basically trying to prove a contradiction. So we are assuming that there is a cycle. So yeah, so now basically it has to violate one of these. So now there's one more observation.
No, at SL, it has to violate, because L is the point, the time, okay?
Yeah, where it goes from basic to non-basic.
Non-basic. And a variable goes from basic to non-basic only if it is, the
constraints are violated. So basically one of these two.
Correct.
Yeah, okay. One of these two should be violated. Yeah, so now there's one more observation, that for any variable that is for any variable xj that is lesser than xr in the variable ordering, so which comes before xr in the variable ordering, we have that lj is we have that its bounds are satisfied. So so why this is true is that there are two cases. Suppose xj is a basic variable. So if xj is a basic variable and its bounds weren't satisfied, then xj will be the one that gets
picked.
The xj will be the one that gets picked, and xr won't get picked. So that's why if it is a basic, if xj is a basic variable, then its bounds have to be satisfied. If it's not a basic variable, then by the invariant itself, the bounds have to be satisfied. So yeah, so either way, if for any variable xj is that is lesser than xr in the variable ordering, we have that it's that the assignment at time step L satisfies both its bounds. Okay, so
yeah, what is the last bullet? I think you skipped over the last bullet. What do you?
No, this is just the explanation for this. So this holds if xj belong to BL, since otherwise xj would be selected to become non-basic rather than xr.
Yeah, I mean, it's not clear to me like why the. It's clear that if it is basic, then properties would hold, but but how? Why would the bounds not be satisfied on non-basic variables?
No, they will. So yeah, so that is from this in. Where did I have the invariant? Okay.
This is it. Yeah, the third bullet there.
Which bullet?
No, wait 1 second.
No, go back.
The previous slide again.
This one.
Okay.
Yeah. So due to this.
Okay.
Due to this again.
Because the pivot and update operation always preserves that. Okay, right in the beginning, it was so. And the algorithm is such that it always makes sure that what is moved into the new non-basic set indeed satisfies this thing, which means it satisfies the constraint.
Okay.
Yeah. Yeah. So now, so now back to what Sir was saying. So since the sequence of states is cyclic, XR must eventually re-enter the basis, because we have that. So we have BL is equal to what we had, BL is equal to BK, right? No, wait, what was it exactly? Sorry, yeah, BT plus 1 is equal to BK, not BL. So if it leaves if XR leaves the basis, then it must eventually re-enter it, since we have this state to be the same after some point. So now let SP be the first state after
But not only eventually, eventually before T plus 1, okay?
Yeah, before T plus 1. So between
okay. Between K and T plus 1, okay? It left at some point L between K and T plus 1, between K and T. K and T, and it has to come back before T plus 1, okay? Because at T plus 1, it is the basic set is the same as in BK, correct?
Yeah.
Yeah.
So now let SP be the first state after SL plus 1, where XR becomes basic again. So that basically means that XR belongs to NP and XR belongs to BP plus 1. Since XR stays since XR stays non-basic in all states SL plus 1 to SP, its value does not change, because the algorithm only changes the values only updates the assignments to the basic variables. It doesn't update, or if it switches. So if the variables that stay in the non-basic set don't have any change in their assignments. And since we are picking SP to be the first state after SL plus 1, where XR becomes basic, that means that XR stays non-basic, and so its value doesn't change. So beta P of XR is equal to beta L plus 1 of XR. Now, so now let in state SP, let XS be the basic variable that is pivoted with XR. So the XS is
go slow there. So Harsh, do you understand this? Why beta P of XR is equal to beta L plus 1 of XR?
I got the idea that if something is non-basic, its value won't change.
That's correct. So, okay, so got it. Good.
Yeah.
So then we can move on. So as long as it is in the non-basic set, it will not change. Okay. So because it's only when it
enters.
When it moves back, will it be adjusted? But as soon as you do that, it is pushed into the basic. Okay. So that's why this thing is. Okay. Go ahead. Yeah.
But,
yeah. So now let XS be the basic variable that is pivoted with XR in SP. So in the state where it goes back, let's assume that XS be the basic variable. So now this is the tableau for XS. So XS is equal to summation of XJ belong to NP, ASJ. So again, here we are assuming this is T. ASJP into XJ, be the corresponding row in SP's tableau. So now, since XS leaves the basis, so again we have that beta P of XS should be violating one of its constraints. So it's either less than its lower bound or greater than its upper bound. So yeah, till here is everything clear? Because now there's just cases and then it's just like some simple calculation. But basically we have these two cases, that beta P of XS is either lesser than its lower bound or greater than its upper bound, as well as these two. That is beta L of XR is less than its lower bound or greater than its upper bound. Yeah, so this is
So
clear.
just remind us all. So L is the time point at which XR switched from basic to non-basic. P is the time point at which XR moves back into basic. Okay.
Yeah.
So and XS is the variable that is used to pivot the XR back. Okay, so that's why these two things, because at that point at P, XS is in violation. Therefore, these are the two possible way of some variable getting violated. At L, which is the in XR was in violation, therefore there were two things. So there are four possible cases to consider. Yeah.
Yeah.
Okay.
Also, just to remind everyone once again, XR is the largest variable in the variable ordering when it becomes such that it becomes non-basic in one of the states, SK to ST. So this is important for the next step. Yeah. So now we can decompose the proof into the following four cases, and I'll only show it for the first case. Then it's just it can be extended very easily. So the four cases are just beta L of XR and beta P of XS, the bounds on those. So firstly, we'll assume we'll do it for this. So we'll assume that beta L of XR is lesser than its lower bound, and beta P of XS is also lesser than its lower bound. So in this case, yeah, so we have beta P of XR is equal to beta L plus 1 of XR, which is equal to LR. So this is because since beta L of XR is was violated like this, it would be updated to be equal to LR, and then the assignment wouldn't change until it is shifted back. So it shifted back at beta P. So beta P of XR is equal to LR. So this is this part. Now, yeah. So since XR is chosen to enter the basis in SP, and beta P of XS is less than LS, so we must have this. So this comes from, I think it's worth it to go back to the algorithm.
Yeah.
Yeah. So we have, yeah, in this case, Xi is equal to XS and Xj is equal to XR. Xi is the XS is the basic variable, XR is the non-basic variable. So we have, so in our case, we have assumed that it's lesser than its beta XS is lesser than its lower bound. So we have this case with us. So to select, so now we select the smallest non-basic variable Xj such that and we also have that beta, let me just write it down. We have assumed that this is lesser than its lower bound, and beta P of X R is equal to LR.
Correct.
Yeah. So now since it's equal to LR, it is, yeah, we have it is lesser than UR. Yeah. So now we have, so for this to be selected, we have to have ASR, AIJ is in this case ASR. ASR has to be greater than 0. Is that what?
Like this, yeah.
Yeah, ASR is greater than 0. So that's where this comes from. Now, yeah. So now what we'll try to, so we have this equation. So this equation is basically, we have XS is equal to summation of Xj belong to NP ASJ Xj. This is the equation from the tableau for SP. This is satisfied by any X such that AX is equal to 0, right? So for any assignment that satisfies AX equal to 0, it also satisfies this, because this is just basically a maneuvering of the variables. It doesn't change the equation. So now it is then, so this is satisfied by both assignments beta L and beta P. So this equation then holds true. That is beta L of XS minus beta P of XS is equal to summation of Xj belong to NP ASJ into beta L of xj minus beta p of xj. Okay, yeah. So as this,
so that is obtained simply by applying beta.
yeah,
on both
by
sides.
applying beta on both sides. Yeah.
Both sides, and that's one. So he's what Amir is doing is, so this kind of equation by plugging both beta L and beta P, and then taking the difference is showing that this equation, which should be true, will be violated. Okay.
Yeah. Yeah. Exactly.
That's how the contradiction is derived. Yeah. Okay.
Yeah. So now basically what we'll show is that this is, I think we'll show this is positive, and we'll show that this can never be positive. This will end up negative. So there's a contradiction. So that is what we'll try to show. So yeah. So first we'll show that beta L of xs minus beta p of xs is positive. So to show this, so like I said, xr is the largest in the variable ordering. So xs is lesser than xr in the variable ordering, which implies that
one thing that you should point out, this is the clever part of the proof, I thought. Okay. So the way that, I mean, I guess maybe there are several ways of showing obtaining the contradiction, but in this particular proof, he chooses, of course, the fact that any beta has to keep at any point has to satisfy the equation. So that is one being exploited, and that this difference, okay, it takes this and then kind of argues that this will be different, and this equation can never hold good. Okay, if indeed if everything moves back, okay, creating a cycle, this will not hold good. Yeah. So that I thought was a very clever thing. Okay, go ahead. Yeah. So, and I think that is important, for at least when I read the proof, this was important. Okay, to the way that the contradiction is being derived. Yeah.
Yeah. So this is definitely an interesting part of the proof. So yeah. So we have that xs is less than xr in the variable ordering, as xs is going from basic to non-basic, and as we said, xr is the largest variable that goes from basic to non-basic in sk to st. So this implies that
is by chance. Yeah, by definition.
Yeah, by definition of xr.
Correct.
Yeah. So this implies that the assignment at time step L for xs has to be satisfied. So this is from this same observation that I had here. Yeah. So this is from here, that for any variable which is lesser than xr, we have that beta L of that variable satisfies its constraints. So that's all I'm showing here. Yeah. So we have this, and now since we have assumed that beta p of xs is less than ls and beta L of xs is greater than or equal to ls, so this is positive. So right now we have proved that this part is greater than, not greater than or equal to, it's just greater than 0.
Yeah, greater than 0. It has to be positive.
Yeah, it has to be greater than 0. It has to be positive. Now, yeah, so now there are 3 cases again. So
once again, can you explain why that is positive? Just want to. So why should that be positive? Do people understand? So can you explain it to me again? So beta L of xs, beta L of xs is.
So this. So this part we basically got from here. So like I said here, for any variable xj that is less than xr in the variable ordering, correct, we have that beta L of xj satisfies its upper bound and lower bound.
Therefore, go back. Yeah. Yeah. So be at L, xs was indeed satisfying its thing. Therefore, this has to be between ls and us. Okay.
Yeah. So it has to be greater than ls, particularly since we have assumed that beta p of xs is less than ls.
Because that's the case that you're considering. Okay?
Yeah. So this is dependent on the case that we're considering.
Correct. Because since you assumed this one, correct. And beta p of xs is.
Yeah, so beta p of xs is from the case, beta L of xs satisfies its bounds.
Okay. Yeah.
Yeah, so therefore this part is positive.
Positive, okay.
Yeah, so now we want to show that what we'll get is that this part is negative. The RHS is negative is what we want to show. So we'll take each for each xj, we'll show that for each xj we'll show that ASJ into beta L of xj minus beta P of xj. We'll show that this is less than or equal to 0 for all xj. So for all xj belong to this non-basic set at state sp, we'll show that this is negative, so summation will also be negative. So is less than or equal to 0 is what we'll show. Yeah. So let's assume, we'll take three cases. We'll first take the case that xj is less than xr in the variable ordering, then xj is equal to xr, or xj is greater than xr in the variable ordering. So if xj is less than xr in the variable ordering, then again from that same from the same part we got this from. Same way, Lj is, so beta L of xj also satisfies its bounds uj and lj. And now since xj was not selected to become basic in state sp, that means that, again, we should go back to the algorithm, but that basically shows that ASJ is greater than 0 and beta P of xj is greater than uj, or ASJ is less than 0 and beta P of xj is less than or equal to lj, or ASJ is equal to 0. So this we have, so this we get from the algorithm. Let me just.
That's correct. You have to show them where it is that you get it, because it was being violated. Go back to the algorithm.
Yeah. So this is the algorithm.
It's the negation of this part on line 7. Correct?
Yeah. Negation of this part. Correct. So so this. So since xj, since we didn't pick xj, we have that basically either it should be great. 1 second, what did it say?
Because J was, you picked the smallest. Okay. You picked you picked at P, you picked R to adjust. Okay.
Yeah. Sorry, my bad. Yeah. So at step P, we picked the smallest non-basic variable, that was in our case xr. So that means that although xj is smaller than xr, it has to violate one of these conditions. So that basically means that either so again, this is I think A, S and J, right?
Correct.
Yeah, ASJ. So ASJ should be, if ASJ is greater than 0, then then beta P of xj has to be greater than or equal to uj. Or if ASJ is less than 0, then beta P of xj has to be lesser than or equal to uj. So it has to be the opposite of this. So it should either be lesser than or equal to, or it should be greater than or equal to, or it should be 0, or ASJ should be equal to 0. So in all of these cases, we basically get that. Now, if I go back here. So in all these cases, we have in all these cases, we have ASJ into beta LXJ minus beta P of xj is less than or equal to 0. So that's because, so in the first case, if we assume ASJ is greater than 0, then this is greater than 0. And beta L of xj is lesser than or equal to uj, beta P of xj is greater than or equal to uj. So this is less than or equal to 0. So this whole thing is less than or equal to 0. In case 2, if ASJ is lesser than 0, then basically beta L of xj is greater than or lj. This is greater than lj. This is less than or equal to lj. So this is positive. This is negative. So we get negative, or we get 0. So either way, in all these cases, we have that this side is lesser than or equal to 0. Yeah. Yeah. Yeah, so now let's move to case 2. So case 2 is xj is equal to xr. So if xj is equal to xr, then we already have from here, from here we have that ASR is greater than 0. So we have ASR greater than 0 and beta L of XR is less than LR, because that's the case that we're looking at right now. We're looking at the first case. And beta P of XR is equal to LR. So this again we got from here.
Yeah, by the fact that it stayed till P in the non-basic, therefore it's
correct. And it's the first. Yeah, so SP is the first state where it goes from non-basic to basic. So that is also important. That is why it stays in the non-basic set, so it doesn't change. Yeah. So, so this again, we obtain that ASR is into BL beta L of XR minus beta P of XR is less than 0. This because this is just greater than 0 and beta L of XR is less than LR. Less than LR, and this is equal to LR. So less than LR minus NR. So this is also less than 0. So we get this whole thing is less than 0. Yeah, so this is case 2. So now the last case is that xj is greater than xr in the variable ordering. So in this case, xj remains non-basic in all the states of the cycle. So its value never changes. Same way that we got beta p of xr stays the same in this by the same logic, its value never changes. So beta L of xj is equal to beta p of xj. So this thing becomes 0. So what we have proved is basically all the terms in this are less than. Sorry.
Okay. I think you had the right slide.
Yeah. So all these terms are less than or equal to 0. For each xj belong to NP, these are lesser than or equal to 0. So, and this side is positive, so therefore there's a contradiction. Yeah, so that's for all terms, this is negative or 0. This contradicts the fact that beta L of xs minus beta p of xs is positive. Yeah, so similarly, you can also prove it for all. We have only shown it for this case, for the first case, but it's very simple to just extend the proof to the rest of the 3 cases.
Yeah, but I think in the other cases, I know it will follow something similar, but there will be some changes. Okay, you will have to use different parts of the code, and maybe in this case you showed
So for this,
be positive and so on. So that may change from case
to
case.
So for here we looked at only this part of the proof. Here this part of the algorithm. In some case, you might have to look at this part of the algorithm.
Correct. Yeah.
So and also like which is negative and positive will change. Like we could, so we could have that this is actually less than 0, and we'll prove that this is all greater than or equal to 0. So that depends on the case. So depending on the case, we'll still use the same equality and we'll prove a contradiction. So so this contradiction proves that there is no cycle. So therefore this check terminates. But so that's all I have. Any question?
So to like recap, we first prove states are finite by saying that Tableau, Tableau depends on basic variables, and then we have like beta t is derived from the Tableau. So now the total states are finite, and then we show that the states cannot have a cycle in them by showing a contradiction.
Yeah, correct. Yeah, we take 4 cases and then for each case we show a contradiction. I've only shown it for one case, but it pretty much extends very easily.
Yeah, intuitively, what does this mean? Okay, so which means, okay, if cycle, okay, see, it is possible for if during the procedure, even if it is possible for the same basic set to be produced, okay, I think it is possible that the same basic set can appear. The same basic set can appear in one of the states during the procedure. But if you do,
but the assignments won't be the same. Then beta t won't be
then the assignment won't be the same. Exactly.
Yeah.
Okay.
So that will be
That's the question I was going to pose. So it is not that it is not possible for the variables to get out and then come back, and you can even have the same basics. But if it does so, then your assignments will be different. Okay. Yeah. So good. So that was what that was the like the overall intuition, because there are a lot of details here. Therefore, and since you assume that there was same state appeared, okay, so that is why this contradiction happens if you have that variable ordering. Okay, so that's why it's critical that you picked, I mean, you can pick the greatest one, I mean, to show the contradiction only if there is an ordering, correct?
Yeah. So total ordering was also very important.
I mean, like, I have a feeling like that this proof could be made a lot simpler if you just modified the algorithm, like if you kept track of all the states, and like if there was a cycle, you just choose a different path, slightly different path, and then you won't have to do this whole proof.
But what do you mean? How? Because you are using, you're saying without using variable ordering?
No, I mean, like, it's just an idea that you might. So the idea is to first show that all states are finite. Like we have like finite states, and after that, you just modify the algorithm to keep track of all the states, which sounds a bit too much, but
no. But if you change the algorithm, then your proof will be different. I mean, if that, then you're not proving the thing for this particular.
Yeah.
What do you mean? You can't change the algorithm for the purpose of the proof, but maybe you're because there is the specific way that the thing is being searched. No, so
I mean, like that is true that you won't get the proof for the algorithm, but the newer algorithm will still get the job done, I guess.
That would be interesting. I don't know. I mean, I also found this was somewhat but once you kind of understand the details as to how the once you understand what is the overall idea for proving the contradiction, then the details kind of fall in place. Okay, so but you're right that whether there is a simpler proof, I don't know if. Yeah, I was asking if anybody had seen any other proof, okay, of correctness of termination. See, this rule, by the way, of using an ordering, being the choice for the two variables to pivot between, to be the lowest in that ordering, is due to one called bland, it seems. That's why this particular rule is called the bland rule. Okay, and I don't know what proof he used. So but so the question that I was posing was if Diganta or anybody else here have seen any other, a different proof of termination guaranteed by the use of bland rule, okay, which is using that ordering. Okay, I've not seen, this is the first proof that I'm going through. So I had that question, Diganta, Madhukar.
Yeah, so even I have not seen any other proof. So what you're saying is that here, of course, the ordering is necessary for the proof, right? You cannot have the proof if you just take away the ordering from here.
Yeah, then we can't have.
You cannot have the proof, right? There's no way you can.
Because this bland rule uses that ordering, okay, and this algorithm is based on bland rule. Okay.
Yeah, I think crucially in these cases they're using the ordering is being used in this final contradiction thing. But I think basically what we're doing is, in some sense, we're fixing the variables into the bounds one at a time. So we can use the fact that most of the variables will be fixed when we're looking at fixing the bounds of another variable, right? Because that's what we're using here. We're using that I think excess is going to be in some bound if this one has a lower precedence in the ordering, right? If you go back a few.
So you're saying that
Yeah.
even if the algo doesn't pick the lowest in the ordering to, I mean, if there is no ordering, we should still be able to get a proof?
No. I'm saying that the ordering is crucial.
Correct.
Yeah, because if we have an ordering, can be like, otherwise we can just keep pivoting between two different tableaus with two different assignments. Even that can happen, right?
Yeah.
Correct.
Yeah. I had seen basically this a similar proof, but they had reduced the LP to a much more simpler form, which to like reduce the complexities of the proof by quite a bit and the number of cases and such. But it was basically this proof itself. So there they had somehow reduced the LP into like by adding a bunch of extra variables that reduced it into a form where you didn't have upper bounds and lower bounds. You just only had all of your variables need to be positive or zero. Like all of your variables are non-negative.
Does the proof there does it become simpler? Because here there are 4 cases.
Yeah, the number of
that there are 3 cases. Okay, so there are pretty much 12 cases that you'll have to reason about to prove the contradiction. Okay, so in that sense, this one is somewhat involved. Doing the transformation, is the proof simpler there?
Yeah, it's I think it had a fewer number of cases. It still had quite a few cases, but I think the number of cases were much less than this one, at least not 12 or anything like that. I think there was like 3 or 4 cases there still.
Yeah. Okay, that's the other observation. So this is good presentation, Amaya. So I liked. So that was good effort. Of course, this the number of pivot operations that you'll have to go through before you find a satisfying assignment. I guess the number of iterations, the T that you'll have to go through, there is a number of pivots, very much depends on the ordering that is used. For some ordering, you might converge faster than.
So this worst case complexity is quite bad, right? Compared to.
That's what. So the worst case complexity is pretty much you will end up having to look at for that ordering all maybe see the number of possible, although it's finite, the number of states, configurations, okay? The beta possible values for beta T, possible values for BT, they're finite, yes, but they're exponential, okay? Because BT can be subsets, all possible subsets of your variables, of the set of variables, okay? And after that, you get LJ, UJ, for each possible non-basic, you have this initial assignment or thing. So in that sense, it is exponential. Maybe there are, for some ordering, it may become, you may end up enumerating all of them, okay? So that's why the worst case complexity here of simplex is exponential, okay? Is, what unfortunately this one does well is what everyone says, but the observation and a point I'm observing is that means that you will have to pick the ordering correctly, no? So I'm wondering, just like SAT-solve, like BDDs in SAT-solvers, the choice of the variables that you, which variable you choose to decide first can have a great impact. So how do simplex procedures choose the ordering, okay, in order to apply the bland rule was a question that that is not clear to me. So if indeed the variable ordering, my intuition tells me that the choice of that variable ordering in which you use can impact, I presume.
Yeah, I think.
Yeah.
I mean, I don't know the details of this too much, but I've seen like there is a lot of heuristics that goes into choosing this variable ordering. Like some very specific heuristics for very like certain kinds of problems, which is why most of the in fact, these are all applied from the optimization case, right? So basically, whenever linear solvers are made, they're made in terms of optimization, not just as SAT things. So there, like the objective function is used quite a bit to decide the heuristics about the variable ordering and stuff, like what we're trying to optimize. And another thing that I've seen is that this algorithm actually, I think, is exponential, and you can, I think, like encode SAT in, like you can encode it into integer linear programs exactly. And then if you pass the a SAT query to this algorithm, what it will produce, like you can show that it is always guaranteed to produce something that is going to exactly translate to a Boolean assignment. So for example, if you bound all of your variables as 0 and 1, and like something like A or B or C then becomes A plus B plus C equals 1. Since each of these betas are guaranteed to be always 0 or 1, it is going to always deal with Boolean assignments of variables between 0 and 1. So then if it could, you know, somehow like check SAT by not doing exponential number of things, then we would have had a sub-exponential SAT algorithm. So that's why.
Yeah, no, I know in literature that I've read, okay, that it is exponential worst case, and whether the worst case exponential complexity proof is done by reduction to SAT, okay, but most complexity proofs, you know, a lot of them they do by reduction to SAT, okay, so that may be the case. Anyway, so it's 4:55. So yeah, so that's good. So let's thank Ameya for the presentation, and
yeah, this is really nice.
Yeah, thank you.
So we will see you at 10:30. Harsh is going next, correct? No. Devjit.
Devjit is next, sir.
Yeah, tomorrow. Okay.
So tomorrow 10:30, right?
Tomorrow at 10:30, correct.
Yeah. Okay. So thank you.
So like mine would be later after like the next to next class, right?
Oh, I didn't know. I mean, that is no. I was assuming you would go. Yeah. You're Harsh. Okay, Devjit. Yes, Devjit's asked for tomorrow. Okay, so he's ready to go for tomorrow. Now we have to schedule yours. Okay, during that at a later time. So it can be during the Jan 1st to 7th.
Yeah.
Okay.
Like could it be like made? Jan 2nd or 1st, like because I have some exams. I have only exams till 31st December, I think. So
yeah, so you're saying you don't want it during the exam week. You want it after that, is what you're saying.
Yeah. So
yeah, so that is fine. I mean, but we'll have to arrange for that. But I want to get Devjit's done tomorrow so that we'll have as few things after the thing. Yeah. So there'll be one meeting for the final project presentation. And
hello.
this well, okay. That was
sir, I think we lost you at the last line.
Yeah, I was since I was not present at yesterday's meeting, I was saying that I hope you guys found that you're found yesterday's discussion useful enough for you to be making good progress on your project. Okay.
Yeah.
So we will have tomorrow Devjit going and two other presentation, one final project presentation and Harsh's presentation. Harsh's presentation on 2nd, when they'll have to decide on project presentation for a date during the first week of January. Yeah. Okay.
Okay.